Hello everyone, my name is Jessica Xia. Today I will be presenting my project where I worked on developing and testing a novel fragment-based virtual screening method for drug discovery. This project was conducted under the supervision of Dr. Matthew Shapira at the University of Toronto. First, let me give you some background on the project. Conventional drug discovery requires a tremendous amount of time, labor, and cost. From the initial target identification to clinical trials, pharmaceutical companies invest on average $1.8 billion over 12 years to push each drug to market. One of the first steps of drug discovery after identifying a protein target is lead discovery, done through drug screening, which is the process of filtering through millions of chemical compounds to narrow down a list of potentially active compounds. This first step is crucial in making sure the remaining steps in the drug development pipeline are time and cost efficient. With the enormous library of commercially available drug-like molecules reaching 10 to 11, 10 to the 12 molecules, and the ever-improving computational capacity available, there has been increasing interest in virtual drug screening. Currently, there are two main approaches to virtual drug screening, namely structure-based and ligand-based drug screening. Structure-based drug screening begins with the 3D structure of the protein target, often obtained from X-ray crystallography or nuclear magnetic resonance spectroscopy. Using this protein structure, the binding affinity between a ligand and the protein's binding pocket is then calculated. The computer simulation aims to find a ligand binding orientation that minimizes the overall free energy. Alternatively, ligand-based virtual screening can be employed when there is no known 3D structure of the target protein available. This approach looks for ligands similar in structure to known active ligands, as ligands with similar structures are likely to have similar protein binding properties. While both structure and ligand-based virtual screening have been successfully applied, there are nonetheless shortcomings to each of the two approaches. Structure-based virtual screening is limited by its high computational cost and CPU time in comparison to the number of potentially active ligands it identifies, whereas ligand-based drug screening cannot be utilized when there are no known ligands of a particular protein target. Attempting to overcome such difficulties, my project evaluates a novel fragment-based screening approach that combines both structure and ligand-based screening techniques. The hypothesis is that for any given protein target, this fragment-based screening method can retrieve known ligands from a large library of random ligands more efficiently than the structure-based approach. Next, I would like to introduce the main steps of this fragment-based screening method. Before I start, I just want to mention that all my work was done in the ICM Pro software developed by MolSoft. It was used in this project to visualize protein and ligand structure, as well as perform all the needed operations including docking, filtering, and conducting similarity searches. This fragment-based screening method consists of three main steps: fragment docking, fragment selection, and finally a similarity search. Here's an overview of all the steps. I will now present the steps one by one in ICM Pro and discuss each step more in depth. So again, this is the ligand binding pocket of the MDM2 receptor. Many different fragments get docked into the ligand binding pocket. And here is a view with just the docked fragments. A few of these fragments are then selected to be the template then used to conduct a similarity search. And this is the orientation of the known MDM2 ligand predicted by RIDE, which is the similarity search method. Shown in purple is still the predicted ligand, except now there's also the actual ligand orientation shown in green. and this is how they compare to one another. First, let's take a closer look at the fragment docking step. As its name implies, fragments are very small molecules, with lower molecular weight than the typical ligand. Their size gives them the freedom to bind to the receptor in the most favorable conformation possible, essentially creating a map of all the interactions that a ligand can make with the receptor. In this demonstration of the method, 10,000 fragments from a Life Chemicals fragment library were used for docking. In this library, fragments ranged from 8 to 23 atoms in size, excluding hydrogens. The second step is fragment selection. After the fragments have been docked, this step filters for the fragments that represent the most important interactions a ligand can make with the receptor, and is broken down into two steps. First, narrowing down 10,000 to 100 fragments, and second, from these 100 fragments, selecting just around 4 or 5. Each docked fragment receives an ICM score and an RTCNN score, which reflect how well the fragment binds to the protein. The ICM score is calculated based on molecular mechanics or physical energy terms, whereas the RTCNN score is a convolutional neural net including layers that do topological convolutions and 3D radial convolutions. It is a machine learning technique trained to recognize native-like complexes based only on putative complexes geometries. To normalize these scores, they are each divided by the number of atoms to yield the ligand efficiency. The fragments are then plotted in terms of their ligand efficiencies for the two scores. So here, the ligand efficiency for the RTCNN score on the y-axis, and the ligand efficiency for the ICM score on the x-axis. And the 100 fragments with the lowest ligand efficiencies for either both scores or just one of them are selected for the second round of filtering. In this second round, areas that had a high concentration of hydrogen bonding, shown in the blue circles, or hydrophobic interactions, shown in the red circles, typically where 10 or more fragments gathered, were considered as hotspots. By selecting the smallest number of fragments that satisfy the highest number of hotspots, 100 fragments can then be filtered down to just 4 in the second round. Here's the summary table of the important protein fragment interactions used to narrow down the number of fragments from 100 to 4. The type of the interaction is specified in the very first column, so this can be a hydrogen bond acceptor, donor, or a hydrophobic interaction. The protein column identifies the atom of the protein that takes part in the interaction shown on its left. The fragment column lists all the fragments that interact at the location of the protein atom. The contacts column counts the number of interactions between the fragments and the protein. And the very last column specifies the fragment that is chosen from the list in the adjacent column, aiming to choose the least number of fragments that satisfy the highest number of hotspots. The third and final step is to perform a similarity search to look for ligands similar in structure to the fragment template. To do so, I used Rapid Isosteer Discovery Engine, RIDE, developed by Molsoft. This is a 3D molecular similarity search method based on atomic property fields, APF, with the additional prerequisite of generating the different 3D conformers of each ligand through translation and rotation. According to empiric physicochemical behavior, the APF method is a generalized 3D pharmacophoric potential that assigns property vectors to 7 different pharmacophoric properties, shown here. The 7 component property vectors are assigned to 21 atom types present in the ligand and fragment template. The values of these vectors range from 0.5, which is weak, to 1.5, strong, and can be negative or positive for bipolar properties. APF was shown to be one of the most accurate methods for chemical superposition. In RIDE, pre-processing of the ligands is what allows APF to be used with much greater speed. On top is the fragment template I previously selected for the MDM2 protein. And below are the predicted orientations of the 2 known MDM2 ligands matched to the 4 fragment template. The normalized RIDE score reflects how similar in structure the ligand is to the fragment template. In other words, how similar the purple matches the yellow, and is used to rank ligands as a prediction of how likely each ligand is to be a real active ligand of the protein. I've explained how the method works, and now I would like to present how well the method performs. Mouse double-minute 2 homolog, an E3 ubiquitin protein ligase, is the key subject of study in this project and will be discussed in greatest depth. However, 2 other proteins are mentioned as well: X-linked inhibitor of apoptosis protein and spleen tyrosine kinase. XIAP is also a E3 ubiquitin protein ligase, but interestingly, its results are very different from MDM2. Inclusion of the SYK protein is intended to offer a first look at the performance of the fragment-based screening method on proteins that are not E3 ubiquitin protein ligases. First, I looked at how well the fragment template predicts the actual ligand orientation. What I found was that a single fragment template can accurately predict the binding orientations of structurally different MDM2 ligands. Here I have displayed both the 2D and 3D structures of 3 known ligands of the MDM2 protein. From the 2D structures, you can see that the 3 ligands are structurally very different. In 3D, I have shown the predicted orientation of the ligand in purple and the actual orientation of the ligand in green. And you can see that overall the predicted orientation matches up with the actual. Here are 4 more known ligands of MDM2 that were not shown earlier. I've paired them up in terms of structural similarity seen from the 2D structures. And it is obvious that the first pair have very similar normalized RIDE scores, whereas the second pair received very different normalized RIDE scores. The high normalized RIDE score for the ligand from 5-LAV from the second pair may be biased since the ligand binding pocket used for docking was generated by selecting the residues of the protein neighboring the ligand from 5-LAV. Similar to MDM2, XIAP is also a E3 ubiquitin protein ligase. As the fragment-based screening method works well for MDM2, it may be expected that the same would be true for XIAP. However, the ligand binding orientation predicted by the fragment template was frequently incorrect. Similar to before, the purple shows the predicted ligand orientation, the green shows the actual, and the yellow is the 5 fragment template for the XIAP protein. The ligand from 4KJU was predicted rather accurately in comparison. However, this may be biased since the ligand binding pocket used for docking was generated by finding the protein residues neighboring the ligand from 4KJU. These results are likely explained by the less defined, more shallow ligand binding pocket of XIAP compared to MDM2 and SYK. The more shallow pocket naturally allows the more flexible binding of a ligand, as it is not forced to be confined in a small space, meaning there may be more interaction hotspots compared to a protein with a deeper pocket, making it more difficult for one fragment template to predict the orientation of many different ligands. This explains why the fragment template is a good predictor of the ligand from 4KJU, but is not a good predictor for other ligands, such as from 3CM2 and 2JK7. To assess the utility of the fragment-based screening method beyond E3 ubiquitin protein ligases, the method was also used on the SYK protein. Overall, the fragment template for SYK was able to accurately predict the binding orientations of its ligands. While the ligand from 1xBB seems as though it doesn't have a good match, such cannot necessarily be said as there are no fragments in that area for the ligand to match with. One potential solution would be to include more fragments in that region. However, that would mean including fragments not representative of the most important ligand interactions. Doing so would also increase the time it takes to run RIDE, which increases linearly with the size of the fragment template. In order for this method to work in practice, we also need to know how well can the method retrieve known ligands from a large library of random ligands, and how does it compare to structure-based screening, which is used now when there are no known ligands of the protein available. To answer these questions, RIDE was performed on more than 400 million random ligands and 10 known ligands against the previously selected 4-fragment template for MDM2. Of these ligands screened, 40,000 random ligands and 3 known ligands had a normalized RIDE score greater than 1. Therefore, known ligands were enriched more than 3,000 times by this fragment-based screening approach for MDM2. The 40,000 random ligands and 3 known ligands retrieved from RIDE were then used to perform a second round of both fragment-based and structure-based screening to compare the two methods. Same as before, the fragment-based screened ligands were ranked by their normalized RIDE scores, whereas the structure-based screened ligands were ranked according to their ligand efficiencies calculated by dividing their ICM score and RTCNN score by the number of atoms in each ligand, much similar to the selection of docked fragments. Enrichment curves were generated for each of these ranking methods and they performed similarly overall. However, the RTCNN ligand efficiency was a better ranking method for the ligands as it was able to retrieve an active compound when a drastically smaller percentage of compounds were screened. In other words, the RTCNN ligand efficiency score ranked the active compound much higher up compared to the random ligands. Ultimately, while structure-based screening seems like the better option in this situation, it is difficult to say if the same would be true for other screens due to the limited data. Altogether, the novel fragment-based screening method is effective and drastically more efficient than the structure-based drug screening. To screen 400 million ligands, fragment-based screening would require a total of 7 days, whereas structure-based screening would take an estimated 150 years using the same computational capacity. With this in mind, fragment-based screening can either be used from start to finish, or as a method to filter molecules prior to structure-based drug screening, narrowing down the ligand library so that structure-based screening can be performed within a reasonable time frame. So far, it is known that the fragment-based screening method can accurately predict the actual orientations of known ligands in some cases and not others. In addition, it is able to retrieve known ligands from a library of random ligands reasonably well compared to structure-based screening. Lastly, I explored whether or not this method can be improved by emphasizing polar interactions. Nonpolar interactions are important for the affinity of a ligand to the proteins, whereas polar interactions are important for the specificity of the binding. Attempting to obtain better specificity, polar atoms were emphasized in 2 different ways. First, by decreasing the occupancy of carbon atoms, and second, by selecting fragment templates from a polar fragment library. The occupancy of an atom can range from 0 to 1, describing the degree to which an atom is located at its mean position. Here, the carbon atoms of the 4-fragment template of MDM2 have been set to 1, 0.7, 0.5, and 0.3. As the occupancy decreases, there is less sureness of the carbon atoms at the positions shown, and changing them like so is intended to emphasize the non-carbon polar and hydrophobic atoms. It was found that decreasing the occupancy of carbon atoms did not improve the accuracy of the predicted orientation, which stayed more or less the same throughout. However, it did decrease the normalized RIDE score. In terms of drug screening, it is not so much the normalized RIDE score of active ligands themselves that matters, but the relative difference in the active ligands' normalized RIDE scores compared to that of random ligands. To see if decreasing the occupancy of carbon atoms would improve drug screening, each template was used to run RIDE on 1 million random ligands and 10 known ligands. Enrichment curves were then plotted for each occupancy. The results show that decreasing the occupancy of carbon atoms in the fragment template results in a greater percentage of random compounds needing to be screened to retrieve the same percentage of active ligands. This is because decreasing the occupancy of carbon atoms causes the active ligands to be ranked lower down compared to random ligands in terms of normalized RIDE score, making it more difficult to retrieve active compounds from a library of random compounds. I then compared how accurate the predicted ligand orientation was using a regular fragment template versus a polar fragment template. The polar fragment template for MDM2 was able to predict the ligand orientation just as well as the regular fragment template, despite it having fewer fragments, 4 compared to 5, that cover a smaller area of the predicted ligand. For the SYK protein, the polar fragment template had the same number of fragments as the regular template, yielding predictions that are comparable and at times better than the regular fragment template. Overall, these results indicate that the polar fragment template potentially improves the prediction of ligand orientation. However, whether or not these results translate to better screening results is yet to be determined. Future studies would need to generate enrichment curves comparing the two fragment templates to determine if polar fragment templates yield normalized RIDE scores that better differentiate active compounds from random ones. Overall, the novel fragment-based screening method is effective and drastically more efficient than structure-based drug screening. It can be used on its own or as a first step that greatly decreases the ligand library for further structure-based screening. Future studies should systematically compare the effectiveness of fragment templates selected from different libraries for retrieving known compounds by generating enrichment curves. Similar analyses should then be performed with other proteins to determine for which proteins this fragment-based screening method would be most effective. Specifically, it would be of value to investigate other proteins with shallow ligand binding pockets to see if the findings are similar to XIAP. Finally, it would be important to experimentally test out some of the top compounds retrieved for a given protein to see if some are indeed active ligands. Finally, I would like to thank Dr. Matthew Shapira for being my supervisor. I would like to thank Evian, who is the grad student in our lab who has been helping me. I want to thank the Structural Genomics Consortium for giving us the platform to do this work, as well as the Department of Pharmacology and Toxicology at the University of Toronto for allowing me to participate in PCL 472. Thank you so much for listening, and here are the references.